Okay, so where we left off, we were looking at analysis of beams. We did a pass-fail analysis, and then this is a little capacity analysis. So, you know, that's different things you can analyze. You can analyze the most basic is just whether it passes or fails, right? Whether for allowable stress, if the actual stress is lower than the allowable stress. And then you can also, by setting the allowable stress equal to the actual stress, in other words, you max out the actual stress on it, take it all the way up to the allowable limit, and then calculate what the moment would be that produce that stress. So that would give you the capacity, either the moment capacity, or you can back calculate it into load or whatever. Okay, so that's this example, and you normally would do that for moment, and then you check it for shear. So you assume the moment controls, and then you check it for shear, and usually the shear will pass then, almost always. If you had a situation of a short span or a very heavy load, then maybe shear would control, and then what you'd have to do is either pick the next highest side, probably just fails by a little. You could pick the next, well, let's see, no, then you'd, if you're doing the capacity, then you'd have to calculate it based on the shear strength and find the end reaction, and then the shear at D, and then calculate the load based on that. A little bit more trouble maybe. Okay, so here, this lovely example. This is supposed to be 6 feet. I couldn't find one that was quite 6 feet. It looks more like 5 feet, but close anyway, if I don't fall over with it. A little 2x4, right? And the question is, how much load can we put on a 2x4 before we'd be in danger of failing it? And of course, this is going to be, what we calculate here is the allowable load, so the safe load. So it's not actually the moment where it's going to fail, but it's the safe capacity of it that we'd be calculating. So certainly I could, right, stand on this if I don't fall over. Okay, so so a point load of my weight, like maybe 150, 145, certainly is within the limit. But how much higher could we go? Could we get two of you to stand there? Maybe, I don't know. So this is based on a spruce pine fir. Whoops. Number 2, which is what that actually happens to be. I'll say that I'm going to stand on it for 10 minutes, okay, just to give it some load duration. Would be a fairly short one. So this might be, you know, if you were going to hang something, lift something from it, maybe, I don't know. But we just want to find the capacity. So spruce pine fir number 2 looks like the bending is going to give us that 875. That's that number, and the shear would be 135. So those are those two numbers. Then we got to put the CDs. So this is the adjustment factors on it. So this is for 10 minutes, right? I think that's what wind load is, if I remember. And then we also want the CF. It has doesn't have any moisture problem, so it's dry. It's at normal temperature. We'll just assume here. It's a 2x4. So if you remember, a 2x4, I don't think requires any bracing at all. So that would be 1 for a 2x4, right? CF we do have to look up. There will be a CF. It's not being used flat. It's not incised, and there's only one. It's not repetitive. So there are not many factors that would actually apply here in this example. Here's my my 10 minutes. So there's the CD factor, and then CF. Well, let's see. We've got number 2. We've got a you can read this, a 2 by 4. Okay, so that would give me, whoops, that would give me that 1.5. So there are my two factors multiplied on. So that gives me my adjusted allowable. Now I would look up for a 2 by 4, the section modulus, and then calculate the moment. So I set the allowable equal to the stress, and then based on the maximum allowable, calculate what the moment would be. So this is the section modulus for the 2 by 4, right? And that gives me that moment in inch pounds, and I'm actually going to calculate it right in foot pounds, I guess, by its dimensions in feet. So I'll convert that, divide that by 12, bring it down to foot pounds, 536, and then that would be the moment, right, is 536 foot pounds. And if it's a point load at the center, PL over 4, I can calculate P. So that's pretty straightforward. 357 is what it ought to carry. That little, if it were, actually it's only 5 feet, but if it was 6 feet. So it easily carried me. It would probably carry a couple of us, I guess. 3 of us might be a little bit dicey after 10 minutes. So we'd stand there for 10 minutes and then we'd hear it start to crack, I guess. Something like theoretically, anyway. Then you'd check the shear. The shear does have the CD factor on it, so that pumps the allowable shear way up, 216. So if I just take this value and use it to calculate the Vmax, I can check this based on the Vmax, which would actually be, in this case, a point load. It would be the same as at D distance. And that only gives me an actual shear of 51. So 51 is certainly safe. Okay, so that's a simple capacity analysis. Now, just for fun, we could take this, as long as I got this thing up here. What if I turn it sideways? How much, I mean, now, watch this, you probably will see it deflect. Whoa, a little bit. I even heard it crack a little bit. Could I stand on that for 10 minutes? Okay, so now we've got same CD factor. Now we've got, well, there's same CF. We've got a flat use factor, so we pick up 10% for flat use. But the big change is my section modulus drops a lot, right? So this goes to, oh shoot, I should have brought my calculator. Well, when you guys, yeah, you're going to have to calculate this for me because I didn't bring, this would be 875 times 1.6 times 1.5 times 1.1. What does that give us? Somebody want to back him up there?
2003, 210.
2310. 2310. Okay, does that look about right? What I had before? What did I have? Yeah, 21. Okay, yeah, all right, I'll believe you. That's PSI. Okay, and now we want to say that 2310 times this 1.313, whoops, except this is in PSI, right? Well, that's right. This will come out in inch pounds then. So what do I get with that? Three something.
3,033.
Okay, and that's in,
Point.
well, points, okay. That's in inch pounds. So then divide that by 12. Let's put it back into foot pounds. And what do I get?
252.75.
Okay, that's in foot pounds. Okay, and then we want to get P, so that would be the 252 times 4 over, and we'll say it's 6 feet. Okay. So that cuts it down a bit, doesn't it?
168.
168. Okay. So if I'm 145, I guess I still make it. 168 would be safe. But if we got two of us up here, it might be a little bit dicey, huh? You think we'd crack it? Should we try it? we could try it after class. Two of you can come up and try and stand on it and see if we break it. Of course, you have to stand there for 10 minutes. That's the, because we're pumping it up by 1.6 by the, for that 10 minutes. But anyway, okay. So you kind of get the idea. Now, this is another analysis example. In fact, I think it's the next homework problem, although it's numbered 3. We skipped one. Yeah, I told you we skipped one this year. So this one is the one that's probably due this coming weekend then. And it's the main point that we'll look at with this example is calculating which load combination controls, how you determine controlling load combinations and still take into account the load duration factor, because the load duration factor, of course, you've got different load duration factor for every combination or different combinations, and then that affects the stress, so you've got to somehow account for that when you're choosing which combination controls. And the way you normally do that is you find you find all the different load combinations, the moment for each different load combination, and then divide that moment by CD, and the one that then controls in that case would be the controlling load combination. So, okay, here we go. What we're doing is analyzing one of these rafters. The other interesting thing about this is we've got projected loads, like the roof live load and the snow load are both projected loads. We've got the dead load here, right, which is actually on the surface. I mean, it's the weight of the thing itself. And then what I don't have a picture of here, we also have the wind load, right? And the wind load is perpendicular to that surface. So I could take in calculating the wind load, I want to take this, I mean, it's a load on that full length, right? Like that. So I've got three different types of loading. And the best thing, normally, if you can do it, it's convenient to convert the loads into projected loads. So this dead load I could convert into a projected load just because it's still straight down. I just have to shorten it, right, to the projected length. So, oops. Sorry, choked on my cough drop. Let's see. So the loads are given here. The dead load is 14. Okay, so there's the dead load at 14. The spacing of the rafters is 16 inches on center. So the first thing we have to do is convert the PSF load into PLF on the rafters. So I've got my PSF load is what it's given in, and then I'm going to convert it down. It'll go up a little bit because I've got the rafters spaced a little bit wider than a foot on center, so 16/12. So that gives me the PLF on the rafter. Now for the dead load, I then want to convert that. It's on an 18.02 length, right? 027, and I want to reduce that to a 10-foot length. So it's as if I'm taking that load and I'm just going to squish it down to fit on 10 feet, the projected length. So I factor it then by 18 point, the full length divided by that projected length. So that gives me then the projected load for the dead load. Okay, so there's my dead load projected. The live load is already on a projected length, right? That's the way we figure the live load is projected. So that's given as 12 PSF, and I convert that to 16 on center, so that gives me 16 PLF. Okay, that's easy enough. Snow load also is projected, so there's my 20 PSF snow load. I simply put that on the joist spacing, and that'll give me a little bit more, 26. Okay, so all of those are projected then. Now, the wind load, here's my wind pressure. The wind pressure is on the actual surface of the roof, right? And it's the pressure is normal to that surface. So I want to take as far as calculating the moment, it's that actual length, the load. It's not coming down, it's coming normal to it already. So I take that 18 point, where'd it go? Well, all right, this just, yeah, I'm not calculating the moment yet. When I calculate the moment, I'll do that. First, just to get that on the rafters, I convert that to 16/12. So that would be 26, but it's 26 on the full length, right? So that's on 18, whatever it is, 03 feet, right? Not the projected length, but the full length. Okay, so now I've got all those. I can look at the moments that each of those will produce. And again, just to reiterate here, we had, this was the dead load, right? And we converted it to that. This is the snow load and the roof live load, and this would be the wind load, is that one. There is also a component, well, yeah, actually, there would be, for the wind, it would only have this. I don't think it has the horizontal component. Yeah, would be not in this case, because the wind is coming in normal to the surface. So this is the wind I've already gotten, is that 20 PSF, right? Okay, so we've got all those, and now we can calculate the moments. So these are the moments for each of these. So I take the load, okay, the projected load, and the projected L, right? So here's the PLF, and this would be in feet over 8. So WL squared over 8. That gives it to me for the dead. The this is supposed to be roof live. The snow load, and the wind load is the one that's different. The wind load's on that full length, this length. Okay, but I can calculate. I nonetheless get the moment for that one. So I've calculated the moment in foot-pounds for each of those loads, and now I can just add them together, right, in the combination. So according to the ASCE 7 here, these are the combinations for ASD that I want to consider. So we got dead load. There's the dead load, right? That's that guy. And that gets a CD fact. So I take the moment, right? I'm taking the moment. It's the moment divided by CD is what I'm calculating. So there's the moment divided by the CD factor. So that gives me a number. Then I take the, okay, this one we don't have any live, so that one's out. This one I've got roof live, so I can take that would be that one, right? So there's the dead and the live, and that takes the factor of the roof live, which is 1.0. Is that right? Suddenly doesn't seem. Every once in a while, you know, you're in the middle of these presentations and you see a number and you think, is that right? I'm not quite sure that is right, but I'll double check it. What do you say? If I can find it, what the heck? Oh, there it is. Live load. Construction load. No, this should be the roof live load. Ah, somebody made a mistake. Okay. What do you know? How did I manage to do that? Where is this? It's on this one. If that's the roof live, that should be 1.25. Okay, well, that makes that a little bit lower then, right? So that would be, somebody calculate that. Take 496 divided by 1.25.
It's 496.48. 496.
No, it's got to be smaller than that. 496 divided by 1.25. Oh, it's got to go. I'm sorry. What?
397.
397. There we go. Okay. So that's even lower. Okay, so that one's not going to control in any case. Dead load plus snow. Okay, that one at least I got right. Okay, so there's the plus the snow. That's from that case. That would be 655. Okay. And then we've got dead plus 0.6 times wind. Where's it? Okay, the rain is out. We're doing rain. Here is, okay, this has got live load on it, so we're not doing live load. And this would be 0.75 times the same thing up there, so that's not going to control. This one would be the next possible one, 0.6. Okay, so there's 0.6 times the wind, okay, divided by the factor for wind is 1.6. So that gives me 669. And then we've got these cases down here. So we've got the live load's not in it. The 0.75 times 0.6 times the wind, Okay, so that's that guy. This is the dead load. Okay, and this is 200. What was 200? The roof live. So that's that one. Okay, so that's that combination. Whew. Okay, and the controlling one there is wind. So that's 1.6. So you always take the CD for the shortest duration, right? So if wind is in it, that'll be it. Or snow, or whatever the shortest duration of the combination is. Okay, and then the last one. Okay, this would be with snow, right? This is my snow load. So there's that whole thing again with snow. And then this dead 0.6 and 0.6. No, that'll be not as severe as that. So that one's not going to count. Okay, so that's all my cases. This was the last case. And then you look at these numbers that you've calculated. Whoops, not that one. That one. And you choose the largest controls. Okay, so that would be that guy. So all that is simply to determine what your controlling load case is. Okay, so this isn't you don't use this number then for anything except to determine the load case. What you want to, the number you will use is this number, right? That would be the moment, which should be this number, right? So this part on top, the moment, from that load case, then should be that 1158. So that gives us then, we know which is the controlling moment. We still have to put the CD factor on it. We also know this is going to be my CD factor, right, when I get to using it. But the moment is 1158 from that load combination. Okay, so it's a bit to go through to decide, but you can see, I mean, this is kind of an extreme example deliberately with the roof because it's got all the different loads in it. And you can see you've got several combinations that could potentially apply, right? How many do we have? 1, 2, 3, 4, 5, 6 different combinations. So of those 6, it's not immediately apparent which one would control. I can't think how you'd guess unless you actually went through this calculation and then determined which is the controlling one. Okay, so we got it. So that's the controlling one. It is repetitive. These are the rafters, so we get to use 1.15. It is apparently a 2x10. Seems to be our favorite piece. Seems like every example we do is a 2x10. Number 2, a 2x10. Okay, so that gives us this guy here, 1.1. Okay, and what do we got? I guess Western Cedar. I forget. Number 2. A Western Cedar, number 2, gives us 700 for FB. So the base, the tabulated stress is 700. And now we put the factors on it. What factors do we got? We said we had CD. We don't have moisture. We don't have temperature. What do we do about CL? About that. CF is this one here. I guess I'm considering it, this is a 2x10, and I must be considering it braced by the roofing, right? So compression edge fully braced. So that would be, we'll take 1.0 for that. And then, all right, that's CF. And here's the CFU. No CFU, no I. Here's R. There we go. That's that one. Okay, so we multiply those on there. This was for the wind, right? This is wind. And we come up with almost doubling it, more than doubling it, right? 1416. Okay, and then Let's see, this was the moment that we calculated, right? This was our moment from the combination. We converted into inch pounds, divided by the section modulus for this was a 2 by 10, and we'll come out with a actual. Then we compare the actual to the allowable, and it looks good, right? In fact, holy smokes, 6 to 14, it's way easily passes. So you could even ask yourself, okay, if you had a situation like that, these are at 16 inches on center. Is that what we did this at, as I recall? So could I maybe go to 24 inches on center? So could I say 649 times 24 inches on center and divide out the 16? And what does that give me? Somebody calculate that for me. Right, this is the actual. So I'm just adjusting the actual stress to a different spacing, right?
973.5. 973.5.
Okay, all right, that would be, so that's still way, no problem, less than the 14, 16. So looks like it was pretty much over designed. Probably could have gone to a smaller size, maybe, I don't know. Anyway, that passes, and then you could check the shear, calculate the shear the Vmax, and hopefully that passes. Okay, so what do we got left here? Another capacity. This is a capacity based on the live load capacity. So this would be something you'd potentially want to, be in a situation where you might check. If you had a given floor system and you know what the dead load is on it, and you just want to see if it meets the occupancy load. See if you have enough capacity to use it as a, I don't know, say it's a bedroom or something, you want to have 40 PSF or 30 PSF, whatever those rooms are. Okay, so you'd want to check the live load capacity in this case. And this, it looks like it was another homework problem, but I don't think it's one this year. Maybe it was from a couple years ago. So this is based on Doug First South, grade number 2, another 2 by 10, seems to be our favorite wood. The joist spacing on center is 24 inches on center. The span is 10 feet. So this is, I guess the full span is 10 feet, and it's braced at the half point. Okay, so maybe we'll calculate CL finally with this, assuming we only have half point bracing and that somehow the floor is not bracing it. The dead load, which includes the joist, is given as 13. So if we take that as the given, then the question is, what is the live load? How much live load can it carry? So again, we want to set the allowable equal to the actual, and then calculate a moment based on that maximum stress, right? So what do we got here? Doug First South, number 2, looks like 850. Is that right? For the bending, and real high, 180 for the shear. Okay, other numbers we'll probably need, if we calculate CL, I think we'll need some of these numbers here too, probably. Okay, for a 2 by 10, right, we've got the area of 1388, we got that one, and the section modulus of 2139. These are going to be the the potential factors that we apply, the ones that actually apply. Let's see, it's repetitive, so we got that one. For the 2x10, again, have this one memorized here. It's 1.1, and this is for floor live load is 1.0. Okay, so we got those. Moisture, it will not exceed 19%, so we don't need a moisture factor. It's not flat use, and this was the guy that we just picked here. Okay, so we got those. That looks good. Now, the one that we've not been doing, but maybe we will this time, is calculate a CL. Okay, if I assume I'm only bracing it at the center, right? I had a 10-foot span, and I'm bracing it at that center point, right? So I've got an LU equal to 5 feet. So there's my LU is that half span is where it's braced. And okay, so that's 60 inches. D for the 2x10 is 9.25, so I can take my LU over D, and that comes out to be 6.4, which is less than 7. So I'm in this category. It's not a cantilever. Uniformly loaded looks like it's this guy here, right? Uniformly distributed load, no concentrated point loads. Okay, simple span. So I calculate that, and I come out with an LE in inches, 1, 2, 3, and then I plug LE. Now I go in here, here's my LE, so there's what I just calculated, the D from the 2x10 and the B, and that lets me come up with an RB. You make sure that that is less than 50, right? So that looks good. You can kind of gauge where it is, what you'd expect for a CL, depending on that number. Like if it's very close to 50, then you'd expect a very low CL, right? As RB is less slender and becomes smaller, then CL goes up and gets closer to 1. So if you had like an RB of 10, you'd think CL's got to be very close to 1.0. In this case, it's kind of in the middle, okay, but I think the graph of it, if I remember how it goes, it's one of these graphs, right? So that, cut that out. So that if this is RB, and this is CL, right? So this would be 1.0, and this would be way down. This would be 50, right? I keep hitting that edge. Sorry. And this would be 50. So you get a picture something like that for that equation. That's what, if you graph this equation. So you can kind of guess, you know, it's going to be less than 1, right? And then you've got to go through this whole calculation. I mean, it is a little bit. So you calculate FB asterisk, that's got the CF and CR on it. It's not got, well, we're not using the volume factor anyway. It's not got flat use, okay? So we're not using flat use. So that gives us the asterisk. That's where that one gets stuck in here. And then we've got to get the Euler stress here. Here's where I wanted that E min. What I say it was, 400 and something. See if it's written over there somewhere. Right? That was the number for E min. RB squared we just calculated. So we calculate that, and we get, looks like 1039. You find this ratio, 0.9, and then you just run it through this equation and come out with a number, 0.8. Okay, so apparently this was 0.8 right up there. Okay, so we got that. There's the CL we just calculated, no moisture. This one we did for the 2x10. Repetitive it is, and this is for live load. Okay, so we got all those, multiply those through, get our allowable bending, and now we want to calculate the moment based on that stress, right? So we want to say the moment times the stress times the section modulus, and we've got this moment already given, right? There's the dead load. So we could calculate this. Wait a minute, let me see. Make sure I do this right. First it calculated the moment. I guess I got the total moment. So there's the allowable stress and the section modulus for the 2x10, and that gives me that moment, and then I convert it down to foot-pounds, right? And that would be, that is the moment, the center line, and then that's equal to WL squared over 8, and I'm trying to find this W. Okay, the part of the W I already know is that 26, so the total here, okay, I just solved this for W, right? The total is 123 PLF apparently, and then I'm going to subtract off the 26, which I've already got in dead load. So what that leaves me is 97 PLF. But then it has a 24-inch. This thing was based on a 24-inch spacing of the floor joists. So that comes out in terms of PSF on the floor, cuts it down to 48. It'd be half of that, right? 48. So, okay, easily would make your bedroom load, I guess. Residential loads would probably be less than 50, right? Would be 40 something usually. So, okay, that would be then the live load capacity. And then you can check the shear. This just puts in the, based on that PLF load for the live load and the dead load, and calculates a maximum shear and checks that. Here's the shear stress then, 3/2 V over A, and that's easily passes the 180. Okay, so that passed the shear. So you could still maybe check deflection, but that would be the live load capacity then for that guy. Okay, how are we doing for time? Oh, a lot of examples in this thing. Design. Okay, finally a design example. Let's do a design example. In design, these have all been analysis so far. We want to find the member size, right? Okay, so to get the member size, we've probably got to find, solve the moment equation, or the stress equation in terms of the section modulus, and then go to some table like this and pick a section modulus. You know, when you do this in steel, because you got so many shapes, they actually give you a table that's set in order of the section moduli, right? So you can start at the bottom and just go up, and they even they even group them in nice little groups. Well, there are not that many. There are not that many options in wood, so it's not really worth making a table like that. So they just put them in here, and you can just come through this and pick one out. I mean, you're picking them out basically of these numbers here, and you kind of know the range anyway. You know, because you want to bound. There'll probably be a selection. You know, you could have a real fat one that was not so deep, or one that's thinner that is more deep. And normally the more efficient ones are going to be the narrower, deeper ones. Those would be more efficient, right? In terms of carrying a moment. The only danger is that as they get real thin, then maybe they get CL might go up. You know, if it gets so thin that it doesn't meet those bracing requirements, and you know then you lose stress because of stability. But okay, should be pretty simple. Very simple example initially. We just want to find the joist size here, right? So we're given the load, given the wood, given the span. In fact, I'll even assume I've got all the factors here. Won't go through all the factors, but just assume that our a factored allowable is at 1,000 psi, and the shear is at 100 psi. We've got a span of 12 feet. Okay, the dead load plus the live load is coming on at 80 PLF. So that we could quickly calculate a moment. WL squared over 8 would be 1440 foot-pounds. And then we could take that, the 1440, convert it into inches. So this is in foot-pounds, and this gets it into inches. This is in inches. PSI was the given amount here, and we come up with an SX, right? 1728, that easy. So then we just come over here and we try to find 1728. So that one would fail. It looks like, wow, have we got to go that big? 17, 16 fail. Well, wait a minute, what am I doing here? Oh, I'm reading the areas. Okay, sorry. Reading the wrong things. See if I can. Oh well. Oh well, that's all right. 2 by 10 is 21. Okay, so 21 passes that. So this one would pass. 13, 14 would fail. That would fail. All these would fail. But this would be the first one passing. So 2 by 10. Okay, there we go. Got to read the right column. 4 and X, right? Okay, SX. Okay, so that passes, and the area is 1388 for that. And we use that then to calculate the shear, right? V over A. So if I take my end reaction was 480, and calculate the stress based on the end reaction, it passes. It's less than 100, so that's okay. So you could still check the bearing, I guess, and deflection, but that would be so simple design example. And here's another one. What's the difference with this one? Another joist. Wood beam design. Maybe this is this one of the homework problems? Not good. Almost looks like one, doesn't it? But I'm not quite sure this is or not. So I can check that out. So here, yeah, we are assuming that it meets that. So CL is equal to 1. We have these factors are all equal to 1. Okay, so in this one we do compare the, we do look at the deflection maybe. check the deflection limit. All right, well, all right, that's a little bit added thing there. So we've got hem for number 1. This is 20 feet, right? 12 foot on center. These are the, or 12 inches, sorry. Moisture content we made, and these are the loads, 7 and 35, dead and live load. Okay, let's see. So here we go. For the hem fur, we've got, this is number 1. Those numbers are the allowables. We got the, yeah. So in terms of picking a CF, right, we don't really know the size yet. So it's maybe, as a guess, somewhere in that range. So CF could be anywhere from 1 to 1.2. So I don't know, you could guess 1.1. It seems to be most of them are 2x10s. Maybe we could guess a 1.1, or you could just take it as 1 and factor it in later. But that one is the one factor you don't know at this point. Right, the other ones you would know. Okay, so we know this was from the live load. This is repetitive. This is the moisture content. There was no moisture. And this is the one that we don't know. So you could say, here it looks like I'm just assuming 1.0, but like I said, you could maybe make a better guess. Okay, so calculating the moment. We've got the loads. This was the dead load and the live load, and it's 12 inches on center, so it comes out to 42 PLF. Put that into this, and we'll come out with foot-pounds, 2,100 foot-pounds. And okay, then we've got to calculate the SX. This was the PSI, right? And this was foot-pounds. So this converts it to inches, and this gives us our section modulus. So a 2x10 would be a little bit low. 2x10 is 21. It's supposed to be 22. A 2x12 would be 31, so that's plenty big. But we've still got to put the CF factor on it. So if I put that CF, it's going to raise it. It's going to raise it by 10%, right? 10% of 21, it's like 2, right? So should go up to about 23, in which case it would pass, right? So I could try this because I'm not sure about that. So I'll try the 2x10 and see if it passes. If it fails, then I know I've got to go to a 2x12. So a 2x10, I add my CF here of the 1.1. This was from the repetitive, I guess. And that gives me an allowable of 1233. My actual is now based on the section modulus here for the 2x10 is 11, so it's under the 1233. So that passes. So it does pass. So I can use a 2x10. And then you can check the shear. Shear easily passes. So the moral is 2x10 worked. And then this one we did a little deflection check, live load deflection. Okay, just for fun. And the limit would be on floor members. I guess that's this L over 360. And that would be it. What? The limit is 0.6, and it looks like we end up with 0.84. Shoot. Okay, so 2x12 or the 2x10 doesn't pass after all. I guess we still have to go to a 2x12 in the end or something. All right. Last one. Okay. Hey, we should be able to get through this. This is, I think, one of the homework problems. It's probably the one not this weekend, but the weekend after. So this is like getting one, we're getting one ahead. Eventually, this would be the one. And this is timber size. This is going to be a little bit heavier member here, right? It has a point load in the center. It's got a tributary area for that point load of this, right? So this is, if this is 19 feet, this must be 9.5 feet. Maybe half of that. 9.5 feet, is that right? 18, 19, yeah, I guess that's right. And then this would be, these are 16 each, so this is a total of 16 then, right? From that to there is 16 feet. Okay, so we got a tributary area of 9.5 times 16, and it's going to have a point load then at the middle. It's got its own dead weight on it, which may be worth considering because it's going to be a pretty big member. It's got a wood density given, so I guess we will calculate the dead weight. Here's a floor live load and dead load, right? So we got those loads times that tributary area, whatever that was. And I'm in the homework problem, it told me to use a width of 13.5. Holy smokes. What? Actual section width. Huh. Okay, pretty stout member. 13.5. We can see, maybe I'll try it with a smaller member first, but okay, that was the suggested thickness. I think in the homework problem it gives you that thickness just to limit the possibilities. So that would be pretty heavy timber, right? We're talking something about like that. It's going to be maybe double that. So maybe, you know, you usually think of proportions like 2 to 1 or 3 to 1. You know, it can be deeper, but still, for a timber, that would be, all right, if that's 1 foot by 2 foot or so, something in that range, I guess, is what that seems to suggest. Okay, we'll see whether that comes out. Okay, so taking that tributary area, multiplying it by 19 plus 35 times this was the tributary area here, and this is the dead load and the live load. So that gave me a point load, right? That's the point load, that. Okay, there's the 11, 24, 8. And then it also has a W based on the size. We could, you know, like any of these things, it's probably saves you a little bit of time in terms of making a mistake first to make a guess. You know, like it wouldn't be a bad guess to, we were saying it was about 1 foot wide, 1 foot by 2 foot would not have been a bad guess, I guess, to at least to get an approximate for the weight, but it doesn't look like I did anything for the weight. Okay, so here's the moment in terms of that point load. Okay, and then we've got the stresses now. Oh, we're in a different table. Look at this. How exciting. Oh boy, wow. We've been in the, up to now, we've been in table 4, right? 4A is all this dimension lumber. But as you get into the bigger sizes, where do we go? Table 4D is 5 by 5 and larger. So this is definitely larger than 5 by 5, so we're in table 4D. If I've got the right wood here, Sitka spruce, and then you've got to decide whether you're a beam and stringer or a post and timber. Post and timbers are within 2 inches of square, right? So this is a beam. This is going to be deeper. It's not square. So it's got to be beam and stringers in here. And what grade am I using? Number 2. Looks like should be 625. Is that what I got? Okay, 625. And the 115. And then we've got these guys too, because we'll probably need that if we got to calculate CL, I think, for a point load in the center. It's going to be braced at the center, I guess. Okay, so here we go. Calculate the section modulus. We got the this, and it's neglecting the dead load, I guess, but okay, close enough. And the stress that we got there, it doesn't, we're not putting any factors on it, so like first time through, we'll do it without the factors. Well, what will we have? We'd have CD would be 1. We can't calculate, there is a CF, a shape factor or whatever, but we can't calculate it until we know the size. So, all right, it's not repetitive or anything, so that's probably not many factors we can put on it that we'd know. Okay, so this comes out to 1025. Where am I? 1020. 10. Wow. 10, that one. Looks like that would, these all fail above it, and then this one would be the next one. I guess these would pass. So those are my options, at least in this part of the table. So a 12 by 24. Okay, yeah, that was about, yeah, it was suggesting actually a 14, wasn't it? Because it said 13 and a half. But all right, let's see if we can do it by 12 by 24. Or these larger 14s. So, okay, let's try this one then. Looks like that might work. We got to calculate CF, and CF is based on the depth D, and our D, what did we just say, was 24? So 24 is greater than 12, right? We've got 24. It's greater than 12, so that would be my, wow, to the 1/9 root. See if you can do that on your calculator. So 12 divided by, this is D here, to the 1/9 root, looks like it comes out to be pretty close to 1. CF is 0.9. Okay. Moisture factor, yeah, it's okay, will not exceed. So that we can take 1.0. Oh, look at this, it's 1.0 anyway. Even in wet surface? Okay. For timbers, I guess the moisture doesn't make too much difference. Flat use we're not doing. Okay, so that looks good. So the only, and then CL, of course. Okay, CL. That's braced at the center line, right? That's supposed to be center line. Is LU of 9.5. LU over D, if I take that as whatever I said there, 23 and a half, is that what I was saying? So that looks like that comes out to 4.8. 4.8 is then less than, I should have the How come I don't have that page up here? Well, you have that big chart, right, with all the equations, and this would be point load at the center. This one, bother, how could I not have reproduced that? This is the, I have to go look myself. All right, where is that? Isn't it in 3? No, CP. There we go. Page 16. This is what I'm talking about. So for a concentrated load at the center with lateral support at the center, that's the case I'm taking. And it doesn't matter at that point, if you look at this, it doesn't matter what your ratio of LU to D is. They're all the same equation. And this equation is 1.11 times LU. So that's where this is coming from. This is table 3.3.3. Okay, there we go. So that gives me an LE, right, of 126. So then I put that down into RB, calculate RB. Whoa, very low RB. Oh my gosh. 4 out of 50. So that's at the very highly braced end, and that's because it's so thick, right? This is a foot wide. So calculate the Euler stress, and then run through that big, there's the other stress, there's the ratio, and I didn't write the equation, but there's the big CL equation. What number is it? 336. Okay, so that's that equation, and that gives us 0.999. Okay, yeah, so not surprising for an RB that small. It would be a very high CL. So CL is not going to take us down much. CF took us down a little bit, not even 10%. And we put those numbers in there. CD was 1.0, was live load, and we come out with a allowable stress, right? Okay, so then we can calculate the self weight. Now we can finally do that based on the area here and the pounds per cubic foot, right, of 30. So that gives me 56 PLF. I calculate the moment based on that 56 PLF. That gives me that. So then I add that in there. There's the dead load moment. This is the live load moment that I had before, the point load, right, from the tributary area. And I come out with a new required revised S 1159. Okay, 1159. Ah! It failed. All that. Okay, it was supposed to be 1159, right? Was what we wanted. So that one failed. So then it looks like we do have to go to a 14. 1159, that one would fail. So it looks like we're down to this guy here. So for the size we've got, 14 by 24. Now I'd have to up the dead weight a little bit, but that's not going to make that much difference. I don't think we'll max it out. We've got 1159 and this is 12, so we're probably good. Okay, so but I did okay, here's recalculating CF. CF, well, it's still the same depth, so that didn't change. CL, not too much change there. That's also the same depth and the same, so that didn't change much. This something in here might have changed the, did this change? No, that's that. Okay, at any rate, that comes down CL is still up at 0.999. And then for that size, there's that. Here are the revised. They're almost the same. Here I have to up the moment for the dead load. I did increase it by the weight of the 14 by 24, so I did pump that up a little bit to adjust that. And this is the SX from the 14 by 24, so the actual stress comes out to be 544, and the allowable is 579. Okay, good. Whew, finally passes. And then you can check the shear. This would just be the end reactions, right? WL over 2, and so that would, the dominant one is this, so it's almost the same as the D distance out, but still, that would be the max, and it's only 29, and you've got 151 allowable, so, okay, that one makes it. And the last thing on this was, I think it did do a deflection check, and this is one that is at least an example showing the sustained versus the permanent. So normal, and this is a pretty common assumption, is that you assume 30% of your live load is sustained, is permanent. So this would be, you know, most of the live load is transient, right? The end of class, everybody walks out, and you're the dominant live load here, but the chairs would stay, and I guess the floor stays. You know, this, I think even this counts as dead load, doesn't it? You know, some of this mechanical stuff, so that's going to be there forever. So there is a 30% of it, I guess you could think, is maybe long term. So we take certainly the dead load portion of it is long term, and the dead load portion of the point load, and then 30% of the live load. So these are my, you know, all the dead load plus the 30% of the live load, and I calculate those deflections, right? Add them up, and then that gets the long-term creep factor. So that would be that's the long-term load. That's that one. That's the 87 here. And then the short-term load is what's left over, the 70% of the live load, the rest of the live load, and that would be that point load, right? So that's the short-term load. That has no factor. So the creep factor here for seasoned lumber, 1.5, we multiply that on there, and it brings us up to, with creep, 0.213. And if we have a limit of L over 240, that looks like that's only, what are the 1912s over 2? Oh, this is the span, right? L in feet, and then converted to inches. So we have almost an allowable of almost an inch, and we're not even up to 1/4 of an inch. So pretty stiff member. That's what you get for a 12-inch deep or 24-inch deep member. Yeah.
Can we also check the 1624 sizes, the bigger sizes, or to see if it's working?
Oh, yeah, I could, you know, rather than, like I stopped at 14 inches. Yeah, you certainly could. You could go to, where's that table? There's 16, 18s, there's even a 20-inch width. But see, I'm getting wider and less deep. So it would be less efficient in terms of a beam. To get the beam efficiency, I want to go deeper and narrower to reduce the area compared to the stiffness. Because as I go this way, my SX is goes up by the cube, right? The cube of the BD cubed, right? Am I thinking it's right? What's that for you? Or is it squared? BD squared. I guess it's squared, right? BD squared over 6. Is that right? BD squared over 6. Okay, so it goes up by the square of the depth. So as I get deeper, the section modulus goes up faster than the area. So as a result, usually I try to limit the width. So that's why I was 12 would have been even narrower, 12 by 24, but the 12 didn't work. So 14, I had to go out a little fatter. 14 by 24 then did pass. I could have gone to 16 by, 16 by 22 looks like it says 1194. And what did I have? I had 12 was what I was trying to get. 12. Or no, that was what that one was. I don't think that was my required one. Where's my... Oh, here it is. 1159. So, okay, yeah. A 16 by 22 might have worked. Okay, but a 16 by 22 has an area of 333, and the one I used has an area of 317. So, okay, not a huge difference. Yeah, not a huge difference. You could go, and 22. Maybe that saves you some headroom, 2 inches of headroom, I guess. So maybe there'd be an advantage to go to a 16 by 22. That's possible. 18 by 22, yeah, well, then there's no point in that. But that would also pass easily. Yeah. But then, you get sizes that big. In truth, you're probably not going to do it out of solid timber. You'd probably do it with a glue laminated member or something. And the glue lams, then there's a whole, several tables on those sizes. Those go quite a bit deeper, and they're stronger too. They have different strengths. Okay, all right, so that gets us through beams. I guess Friday maybe we can go on with columns. Have a look at the next homework at any rate. You can start to work on that. Everybody got the one done last weekend? Okay, good job. All right.